So in this video we're going to go over how to find the distance from a point to a plane. So here's the idea. Suppose we have a plane in three-dimensional space. So here's my one-dimensional representation of a plane. This plane has a vector that is normal to it, and we've already discussed how to find the normal vector to the plane. So it has a normal vector to it. So if the plane is ax plus by plus cz plus d equals 0, we know that that normal vector is just the coefficients from the x, the y, and the z variables. So it's just the vector a, b, c. And then if we have a point P on the plane and a point Q that isn't on the plane, and the point P can be any point, if we want to know the distance from Q to the plane, it's just going to be this distance right here. And the idea is if we find any point in the plane, we can make the vector from P to Q. And then what we can do is project PQ onto the normal vector. So we do the projection of the vector PQ onto the normal vector. So find the projection of the vector PQ onto the normal vector. So I want to know the distance from Q to the plane. Find any point in the plane. Find the vector PQ, taking the terminal point minus initial point. Then project PQ onto the normal vector. And if you do that, that's going to give you, the projection is going to give you this vector right here. That's going to be the projection of PQ onto the normal vector. And the idea is that if we can find the projection of PQ onto the normal vector, we just need to know the magnitude or length of PQ, and that will be the distance from Q to the plane itself. So we need to know the magnitude of that projection. So remember, when we calculate a projection, if we calculate the projection of PQ onto the normal vector, that's just going to be PQ, the vector you're projecting, dotted with the normal vector, divided by the size of the normal vector squared times the normal vector itself. So what we've done in the past is taken one of these sizes and put it under the normal vector. And the moment we do that, we get a vector of length 1, which we've called n hat. And if this is a length 1 vector, then the absolute value of this is the length of the projection vector. And so that's what's going on with the formula up here. It says find the projection of PQ onto the normal vector and find the size of that projection, which is going to be the absolute value of n dot PQ divided by the size of n. And remember, the order of a dot product doesn't matter, so PQ dot n and n dot PQ are the same thing. So if we use this in practice, here's what it looks like. Find the distance from the point 1 to negative 1 to the plane x minus y plus z equals 3. So my graphical representation would be, here's my plane. Here's the point 1 to negative 1. And I want to find this distance right here, the distance from the point to the plane. And so we'll call this our point Q. And so step 1 is just find any point P in the plane. It doesn't matter where that point P is. So the simplest thing to do is to take and set two of your variables equal to 0 and then solve for the other variable. So in this case, if I set y and z equal to 0, I'll get x equals 3. And that means the point 3, 0, 0 lies in the plane. So here's the point 3, 0, 0 lying in the plane. And the moment I know a point in the plane, I can find a vector from that point to the point Q. I'm interested in finding the distance from Q to the plane. So the vector PQ is just going to be given by terminal point minus initial point. So 1 minus 3 is negative 2. 2 minus 0 is 2. And negative 1 minus 0 is negative 1. And then because I have the equation of the plane, I know the normal vector. The normal vector, or vector perpendicular to the plane, is just going to be the x y, and z coefficients. So the x, the y, and the z coefficients gives me a vector that is perpendicular to the plane. So n equals 1, -1, 1. And we just need to find the size, the length of the projection of PQ onto this normal vector. And once we know that size, then we know the distance from Q to the plane. So to calculate that size, instead of finding the entire projection, we just find the size of the projection vector. So it's going to be the normal vector dotted with PQ divided by the size of the normal vector. So this will equal, our vector n is 1, -1, 1. We'll dot that with the vector PQ, which is the vector -2, 2, -1. We're going to divide it by the size of the normal vector, which is going to be a square root kind of guy, and we need to make sure to take the absolute value of this because we want a distance, not a directed distance. And then the size of the normal vector, we know that that's just going to be the square root of the sum of the squares of the vector components. We've already done this, so we plug in the vector components, and when we simplify this, we're just going to get the square root of 3. So this is going to be the square root of 3 down here. We take that dot product in the numerator, so we get 1 times -2 is -2, plus -1 times 2 is -2, plus 1 times -1 is -1. It's all over a square root of 3, which is a -5 over the square root of 3. So the distance is always, distance by definition is always positive. So the distance from the point Q to the plane is just going to be 5 divided by the square root of 3.